On August 30th, 1961, at the Cape of Severny Island, Nova Zembla, the Soviet Union tested the most powerful thermonuclear weapon ever created, the Tsar Bomba, codename Ivan. Its powerful blast yielded an unparalleled 50 megatons, enough to annihilate anything in a 35-kilometer radius. The explosion was so powerful that the light and sound of the blast could be seen and heard from up to 900 kilometers away. The heat from the explosion was so strong that it could cause third-degree burns as far as 100 kilometers from ground zero. Its mushroom cloud could be seen from as far as 161 kilometers away. A truly horrifying spectacle. As far as powerful bombs go, the Tsar Bomba set the record for the most potent ever detonated. Except it pales in comparison to the most powerful explosive known to mankind, with its core no bigger than a pinhead. What would happen if instead of uranium, plutonium and hydrogen, this substance is used? Something so powerful that science fiction calls it the doomsday weapon, destroyer of planets. Hello everyone, Subject Zero here. Neutrons are subatomic particles that have neutral charge. They have slightly greater mass than protons and constitute the nuclei of atoms. They are roughly encountered in similar proportions, usually 50-50. Neutrons can only exist either by sharing space in nuclei, where the strong force helps maintain its characteristics, or with a whole lot of gravity, which is the case of a neutron star. You see, free neutrons won't last long by themselves. Typically, their half-life is about 611 seconds or a little over 10 minutes, and in that time, one single neutron releases 1 million electron volts. But how much energy is that? To answer this question, we first need to establish a comparison benchmark with TNT. Trinitrotoluene is a yellow solid best known for its explosive applications. It was first synthesized back in 1863 by German chemist Julius Wilbrand. Ironically, it was first used as a yellow dye and only recognized as an explosive 30 years later. Due to its stability and power, it quickly became the most used chemical compound for explosive applications, running from the military to industrial and mining operations. TNT is considered the standard comparative for bombs and destructiveness for explosives. It is common to see references of kilotons and megatons of TNT equivalent, like the Hiroshima bomb, Little Boy with 15 kilotons, and Nagasaki's Fat Man with 21 kilotons. To understand how they equate TNT and atomic bombs, we first need to grasp what a unit of TNT is capable of. 1 kilogram of TNT has an energy density of 4.2 megajoules, which is equivalent to over 1 kilowatt hour. With an average household in the US consuming 11 megawatt hour per year, that is enough energy to power it for 1 hour. The heat of combustion when detonated produces 14.5 megajoules, equivalent to 4 kilowatt hour. It can power that same house for a little less than 4 hours. Little Boy's 15 kilotons of TNT equivalent had an energy density of 63 terajoules, equivalent to 17.5 gigawatt hour. That is enough energy to power over 1,600 houses for 1 year. The heat released by the bomb could power even more. At 60.5 gigawatt hour, it could power more or less 5,500 homes for 1 year. Nagasaki's Fat Man adds a little more power, or 88.3 terajoules, with a 24.5 gigawatt hour equivalence, enough to power a little over 2,200 homes, or almost 7,700 homes with its heat energy of 84.6 gigawatt hour equivalent. In terms of destructiveness, both bombs combined would be able to vaporize almost 60 million liters of water. That is equivalent to 23 Olympic pools or 970,000 average male adults instantly at blast radius. The Tsar Bomba multiplies those numbers by almost 1,400 times. That means over 32,000 Olympic pools and 1.35 billion average male adults. As we can see, we could kill over 1/7 of the population on Earth if everybody was stacked on top of each other. Luckily, that is not the case. But is there a way to be more destructive? Well, a single neutron releases about 1 million electron volts, which is insignificant. But if we had, let's say, 1 kilogram, then things become a bit more interesting. In these calculations, we assume that 1 gram of neutron has 6 times 10 to the 23rd number of particles. By that, we can calculate the energy multiplying the result by 1 million electron volt. Then we convert the results into joules and divide it by the total energy of 1 ton of TNT. At the end of 1 kilogram total decay, the full energy released would be equivalent to 11.5 kilotons of TNT. That is almost as powerful as the first nuclear bomb detonated, little boy. Though it releases almost the same energy as the first nuclear weapons, I must point out that the explosion would not be the same. As neutrons decay, it will release all that energy throughout its half-lives. Curiously enough, it would be releasing energy for about 15 half-lives or 2.5 hours. However, there is a caveat. Its density. How dense is it, you may ask? Well, neutronium is so dense that 5 cubic centimeters of it would weigh 5.5 trillion kilograms. That is equivalent to 900 pyramids of Giza on a teaspoon. The substance is believed to exist as the core of neutron stars. I must also point out that neutrons have weak interaction with matter, so capturing them would only be possible through using an anti-gravity stasis field, something straight out of a science fiction book. This is necessary for 2 reasons: one, to stop neutrons from decaying, and also second, to hold them against gravity. We also need to keep in mind that this substance would be in the form of a degenerate neutron gas, not solid. For the sake of an argument, let's assume that we do have the machine, and let's name it Zarina. Also, I will not consider factors like gravitational pull or pressure, among other things. I will only focus on the total energy of the system for my calculations. Lastly, let's also assume that the anti-gravity stasis field will fail at 4 kilometers above the surface. How much damage would a teaspoon of neutronium cause to the planet? Using the same calculation logic as before, you will arrive at this number. This is tons of TNT equivalent. To pretty much all people on planet Earth, this number makes no sense. So let's break it down to more sensible stuff. A good way to look at it would be to compare to the most iconic asteroid impact to ever hit Earth, the Chicxulub impactor, the asteroid that caused the extinction of the dinosaurs. Estimations put the asteroid in between 11 and 81 kilometers in diameter. The impact is estimated to be in between 1.3 to 58 yotajoules. That is 1.3 followed by 24 zeros. That much energy created a crater 150 kilometers in diameter and 20 kilometers deep. 5 cubic centimeters of neutrons is 200 times more energy dense than the Chicxulub lower estimated impact energy, and 4.5 times at the higher end. Ignoring the fact that not all energy would be released through impact, if it were, we could extrapolate that Zarina would make a crater 675 kilometers in diameter and 90 kilometers deep. Another way to look at it would be if we were to take its first half-life energy and then divide it by the number of seconds it takes for one half-life to pass. At the very first second, the energy released by Zarina would be equivalent to 2 million Tsar Bombas. The total area of destruction of the Tsar Bomba is 3,850 kilometers square. Zarina would have enough power to destroy the entire surface of the planet on the very first second. 16 times over. And that would keep happening for the next 610 seconds until its power is halved by only 8 times over. By the time it would take to reach low levels, the planet has already been through 9.5 hours of extreme destruction. Even at this point, the energy being released per second would still be equivalent to 1.5 kilotons of TNT. It would take 5 more hours for the remaining energy to be released and reach meaningless levels, totaling 14.5 hours of pure hell. By the end of this event, everything is destroyed. However, only 11% of the ocean's water have evaporated. At least some good news. Alright folks, that's it. We're done here.